Okay, hello everyone. Let's go ahead and take a look at Bayes' theorem, which is a higher level probability topic. It says that if a sample space U is partitioned into two mutually exclusive events, and let's go ahead and use this diagram to show that. Notice that we have U, which is our sample space, A and A prime, which are mutually exclusive events. And then we have another event B, which is going to be intersecting both A and A prime. Then we have this probability of A given B result, where the probability of B is going to be equal to that result there. Now, this looks a little bit complicated, but basically it is nothing different from the tree diagrams that we've been using, but just expressed in very mathematical terms. Now let's go ahead and see why that's true. Let's go ahead and take a look at this tree diagram, which we're all very familiar with. And notice that what's going to happen is that we're going to actually go ahead and talk about A and A prime, because we know we have to choose A and A prime. And so what we have here is we have the probabilities that are associated with A and A prime in green brackets. Okay, and that's again nothing different from what we've normally done with tree diagrams. Then notice that what we have after that is we have B or B prime. And notice that B and B prime is right, B is right here, and then B prime of course is everything outside of B. And what we have now, take a look at this, it says this is actually going to be the probability of B given A. Now why is that true? Well, the reason why it's true is because we have to go through A to get to B, so therefore this probability of B is dependent upon the probability of A because we went through it. It's the same thing for this here. Notice that this one is the probability of B prime given A because we had to go through A. This one here is the probability of B given A prime because we had to go through A prime. This is the probability of B prime given A prime because again we had to go through A prime. So notice that what we have then is that if we wanted to go ahead and talk about the probability of B, well, as with our normal calculations using the tree diagram, I had to get this branch and add it to that branch, or the probabilities associated with those branches. So notice what I have then is that if I wanted to go ahead and determine the probability of B, that's the same thing as the probability of B given A times it by the probability of A. And notice that that's what that is right there. And then this one says this is the probability of B given A prime times it by the probability of A prime. And notice that that's what that is there. Okay? So that's how we can go ahead and use Bayes' theorem to go ahead and express mathematically what we've been doing with the tree diagrams all this time, given this particular situation. Okay? So let's go ahead and see how we can apply that. Now I'm going to use one of the problems in the book. This is number 1 in exercise 18L. It says coffee making machines, alpha and beta, and instead of calling it beta, we'll call it A prime. Produce coffee in identically shaped plastic cups. Alpha produces 65% of the coffee sold each day, and beta produces the remainder, so therefore 35%. Now it says that alpha underfills the cup 4% of the time. So we have alpha underfilling the cup 4% of the time, which means that it fills the cup 96% of the time. And then it says that the beta or A prime underfills the cup 5% of the time, which means that it fills it up 95% of the time. Okay, so notice that we basically have this situation here, right? We have the alpha and the beta. In this case, it's just A prime. Those are the two different coffee machines. Notice that they're completely mutually exclusive. And then we know that there's one particular event of underfilling, which is going to happen for both A and B, or A prime in this case. So what we have now is we have the conditions that fulfill Bayes' theorem, and so now we can go ahead and just use our tree to go ahead and say, for example, find out what is the probability that the cup is actually underfilled. So in order to do that, I just do this. I multiply those two probabilities together, times it by those two probabilities together, and I know for a fact that that's going to be the probability of the cup being underfilled, which in this case is 0.0435. Okay? Now, when it comes to the probability of A given U, okay, or what is the probability of A given that you know that the cup is being underfilled, instead of using this here, what we're going to go ahead and take a look at is we can still use our ideas or our formulas for conditional probability, and that generally is simpler sometimes. So I'm going to go ahead and do that right now. And I know that the probability of A given U is going to be equal to the probability of A intersect U divided by U, or the probability of U. So what is that? That's going to be this. So that's 0.65 times by 0.04 divided by what we found in the previous step, which is the probability that the cup is underfilled, and I come up with 0.5977. Okay, and if you wanted to round it to 3 significant digits, you could, to 0.598. Okay, now let's go ahead and wrap things up. If we have a particular situation that looks like this, then we can go ahead and use our tree diagram to go ahead and calculate the probabilities that are being asked for. Now the one thing that we haven't done yet is we haven't actually seen why this is true. Okay, and what we'll do is in class, we'll go ahead and take a look at why that is true. Okay, so let's go ahead and take a look at some of those problems the next day that we meet in class, and we'll take some questions as well as to why this is actually true. Okay, so we'll see you the next time. Bye-bye.